Hello, welcome back to the channel and welcome to Code Like a Ninja, Zero to Hero in C# with Tiger at Astronomy, Episode 2, FizzBuzz. Hi, this is Tim and welcome back to Code Like a Ninja. We are going to write a small program in this episode. We're going to use test-driven development to do it, and before we can do that though, we need to cover some of the basics of C# language. So there's a lot to get through in this episode. It's going to be pretty intense, so don't worry if it doesn't all sink in immediately. There is a lot to go over, and we will reinforce everything we cover in this episode in practical examples, either in this episode or in later episodes. So without any further ado, let's look at C#. Every program needs to store and manipulate data. That's kind of the point of programs, and they'd be rather useless if they didn't do that. So the types of data we can manipulate, there are a variety of different types. And in C# there are two main categories of data. There are simple value types, also known as structures, which are things like integers and characters and sort of basic low-level data. And then there are reference types or class types, which is where we will spend most of our time, and these build on the value types. They build aggregations and other kind of data structures. You can build quite complex data structures with classes, and so that's where we'll spend most of our time. But initially we will look at the simple value types. Okay, the value types are, you can think of them as the simple or fundamental types of the language, and they're used to store things like integers or whole numbers, and real or floating point numbers, decimal numbers, which are a bit like real numbers but they're stored differently to give better behaviour in terms of rounding errors, and it's particularly good for storing money and similar items. Then you've got characters and text, and you've got Boolean or logical values, which can only hold the values true or false, and those are good for doing comparisons and logical operations. Then you've got enumerated types, which is a type in which you explicitly list out the values it's allowed to take. So for example, you might have a type called traffic light and you could give it the values red, amber and green. And then you have variations of the above, such as integers can have different sizes, so you can have short and long integers, and you can have signed and unsigned integers, and similarly you can have single precision floating point and double precision floating point, and there are various variations along those lines. So we'll quickly take a look at some how you would use value types in code, and we're going to bring up the C# interactive window, and you can find that in Visual Studio under the View menu, Other Windows, C# Interactive. And what it is a little console window that lets you immediately type in C# statements and have them executed straight away. So what we can do is we can just declare an integer. So we can say int we can have an integer called length, and we can initialize it with a value, say 4, and then you have to put a semicolon. Every statement has to end in a semicolon, and that's not strictly true, but for the most part that is true. And you press enter and that statement gets executed immediately, so that variable's been created in memory and initialized with the value 4. We can create another int. Okay, and then we can create strings in a similar way. So we might say string, in order to print out the value of a variable in the C# interactive window, you can just put the variable name and press enter, and the interpreter will print out the value of the variable. The other main category of data is the reference types, and in C# that means classes or class types. Now, a class type is a template for creating instances or objects, and that's the objects in object-oriented programming. Class definition, the source code of a class, describes a data structure that contains both data members or fields and function members, which can be methods, properties, and a few other items. Now, the data is the information that a class contains. That's sometimes called the state of the class, and the function members contain the code that the class can run on the data that it contains. And one of the neat things about a class is it groups together all the code and data that performs a related operation. So class types support something called single inheritance and polymorphism. Now, these are kind of scary sounding words, but they are one of the really powerful features of object-oriented programming. Now, what this basically means, it's a mechanism whereby you can take a class, either one that you've written or one that someone else has written, and you might not even have the source code for it, but nevertheless you can create a derived class from that, and you can add more data to it and more features, more methods, more behavior. So using that, it actually doesn't sound like much, but it's a very, very powerful feature of object-oriented languages, and it means you can stand on the shoulders of giants and use code that other people have produced and go forward from there. Okay, so once you have a class defined in code, to use that class you must create an instance of the class in your program, and you do that using the new keyword. The new keyword allocates memory, runs the class constructor. Every class has a constructor. You can write one yourself. If you don't write a constructor, then the compiler automatically puts one in for you, so every class has a constructor without exception. And so the new keyword runs the constructor and it gives you back a reference to that instance. Now, this is the word reference here is why these are called reference types, because you never really access the instance directly, you access it via the reference. References may be saved in a variable or passed into a method as an argument to a method. So let's have a quick look in the C# interactive what this might look like. So you can define a class, and the syntax for defining a class is the keyword class. I'm going to call this degenerate because it won't do anything, and then you just put the open and close brackets and press enter, and that has defined a class called degenerate. And it doesn't actually do anything because it hasn't got any data or methods, which is why it's a degenerate class. So you could, for example, have another class called rectangle, int length, int width. Let's make these public, otherwise we won't be able to see them. So this is modifying the accessibility of these fields, making them public so that other pieces of code can use them. We'll cover this later. Press enter at the end of this class. There we go, that class is now defined, and then we can say we can create an instance of that class. So we can say a rectangle. This is the data type. We're declaring an instance of something of type rectangle, and that's just the class name, my shape, and then we say new rectangle. The parentheses are needed because what we're doing actually here is calling a method, which is the class constructor. So we'll go ahead and do that, and that has now created that instance, and we can say we can now access the data members of that class. So when we type dot, the dot notation allows you to specify the member that you wish to access, and you can see that in the pop-up the editor's trying to help us write the code. So it knows that we've defined this class with length and width, so it's trying to help us use those, and Microsoft calls that IntelliSense, which is a bit of a cute name, but there we go, don't shoot the messenger. So you can say we can have a rectangle of length 4, my shape dot width. That's about as far as we can go at the moment, because we haven't covered enough concepts to do anything with that class. But you get the idea. That's how you define a class, create an instance, and then access its data members. Okay, so we know how to create instances of classes, but we need to know about the object lifecycle. So when you use objects in your program, you create instances at runtime using the new keyword. We've already seen how to do that. Now, creating an instance reserves space in memory for it and also runs the constructor, the class constructor. And the job of the constructor is to completely initialize all the data in the class and set it up ready for use. So at the end of the constructor, the class must be fully ready for use. The constructor will do things like setting initial values for all the data members and anything else that's required. You can create as many copies of a class or instances as you like. So typically programs will create dozens or even hundreds or thousands of instances of a class. How do we get rid of them once we've created them? Well, this is a major difference between C#, which uses a technique called managed code, and older languages like C and C++, where you had to do all the memory management yourself. So if in C++, for example, if you create an object using the new keyword, then at some point later on you have to delete that using the delete keyword, and that leads to a whole class of bugs where either you've deleted something and then another part of the program tries to use it and that causes an error, or you can get into a problem where you forget to delete something and that causes a memory leak because the program just keeps using more and more memory until it crashes. So in modern languages like C#, they use a technique called managed code, and the way that works is you create your objects and then you forget about them. The runtime can sort of keep tabs on an object and work out when it's not being used anymore, and when it detects an object that's not being used, it just deletes it for you. So that's done by something called the garbage collector. It's debatable whether that's more efficient or less efficient. It's actually pretty efficient. The garbage collector is a highly optimized piece of code. This is great because in C# we are basically freed up from the chore of doing memory management, so we can safely just new up as many objects as we like, and then when we're done we just discard them and the garbage collector deletes them for us. Okay, if we're going to write code, we need to talk about program flow, and there are basically three ways in which a program can progress, and the three ways are sequence, selection and iteration. So sequence hopefully is straightforward, and that means that you write statements and they're executed in the order they're written. So if we look in the C# interactive window, we can give an example of a sequence. So we can say int a equals 2, int b equals 4, and int c. Okay, and that's a sequence. Those three statements are just simply executed in order, one after the other. And the second type of flow is called selection, and that means you can choose between a number of alternative actions based on some condition. So the probably the simplest example of selection is the if statement. So you write an if statement like this, and then in brackets you write the condition you want to check. So if A is less than B, which it is in this case, we will do some action C equals A, and then you can have an else part and another set of brackets C equals B. Okay, so C is going to be equal to either A or B. Basically it's going to be equal to the lesser of A and B. Okay, and I've written this all on one line because that's just the simplest way to do it in the interactive window. But normally you would put new lines. You would put a new line there and have this all nicely indented, and this would be on its own line, and this part would be on its own line. So, but in the interactive window, the formatting goes all a bit crazy if you try and do that. So I've just written it all on one line, and when I press enter, that code gets executed, and then we can print out the value of C, and C is in fact 2, so the lesser of A and B. So that's selection. And the final type of flow is iteration. That is a way of repeatedly executing code over and over again, either a set number of times or until some exit condition is met, or sometimes applying a piece of code to every piece of data in a collection. And the simplest example of iteration is probably the for loop. So for, and then you need a loop variable, call it I. So typically that's called I or index. We'll just call it I. So for int I equals 0, semicolon. And then the for loop has 3 parts, and the first part is the starting condition, the second part is the exit condition, and the third part is what you do every time around the loop. So the exit condition is, we'll say I is less than C. So we're going to do this loop while I is less than C, and then each time around the loop we will add 1 to I. So you can do that using an increment operator like that. You start a block, and in the block you do whatever you want to do in the for loop. So what we will do is console.writeLine I. We'll write out the value of the loop variable. Okay, and when I press enter, we should see, there we go, it wrote out 0 and 1, because if from up here C was equal to 2. So while the loop counter was less than C, i.e. less than 2, we wrote out I, and then we incremented I, and we went back around the loop. So don't worry about the exact way that works. We'll see plenty of for loops in the code we write later. And so those are the 3 basic types of program flow. Now we can write methods. Okay, a method in C# or any programming language really is kind of analogous to a mathematical function. Now, if you remember from maths, you could a function is a definition of some operation or relation that maps to a set of input values to a set of output values. Mathematical functions are written as shown on the slide here. So f of x equals sine of x squared plus 1. Okay, so this is our example mathematical function. In a formal function definition, which is what this is, x is called a parameter. Now in mathematics, x isn't actually called a parameter, but in code it will be. So for simplification, I'm just going to refer to that as a parameter here. So, and there can be more than one parameter. So you might have f of x comma y equals sine x squared plus y. And hopefully there's nothing new there. You should be familiar with this. So a function is used by supplying specific values for each parameter, and these are called the arguments. Arguments are substituted for the formal parameters, and then the value can be computed. So, for example, the function f of 7, 3 would be computed as the sine of 7 squared plus 3. Okay, so hopefully that's all clear. Okay, so what does this look like in code? Well, functions, or in C# they're referred to as methods. Some languages make a distinction between functions and methods, where functions take inputs and produce a result, and methods just take inputs and affect some state but don't return a result. Languages like Pascal do that. But in C# there is no distinction between a function and a method. Everything is just called a method. Methods have parameters. When you call the method, you supply the arguments for those parameters. The method executes and it returns a result. And methods can opt to not return a result, but they must be declared then in a certain way so that the compiler knows not to expect a result. All methods must declare their return type, so a method can only return one type of data. So for example, it might return an integer, and then once we've decided that, it must return an integer every time, or it might return an instance of a class, for example, but it must always return an instance of the same type. So methods that do not produce a result must declare a return type of void. Okay, so what does this look like? In the C# interactive window, let's turn that on, we might declare a method which doesn't return anything to start with. So test class and open bracket. Now in here we can define our method, and we'll make it a public method so other code can access it. It doesn't return anything, so it returns void. We'll call it does nothing again, and then we have our squiggly brackets. You must have a set of parentheses there, and then you declare any formal parameters that the method takes. Now, the does nothing method doesn't take any parameters, so we just have an empty set of brackets. Okay, and there are two ways, as I was saying, to return from a method. Either you can use the return keyword, or you can just reach the end of the method, get at the closing brace, return is assumed. Okay, I'll leave it in there because it's clearer, it's explicit, you can see what's happening. And then I can say var instance. Now I haven't mentioned the var keyword before, but that's just a shortcut that lets the compiler work out what type you want. So it will look at the right hand side of the equals sign, and if I say new test class, so I'm newing up a test class, and because I've used the var keyword here, the compiler looks on the right hand side of the equals, sees that that expression produces a reference to test class, and so this, if I hover over var, you can see that in the little pop-up there it's telling me what type it has inferred, and that would be class test class. Okay, so I can new up that class, and now I've got an instance of it. I can say instance dot does nothing, and that's calling or invoking the method does nothing on the instance called instance, and then we have to pass it the arguments, and because the method declared no parameters, there can be no arguments, so we just have again an empty set of brackets. Putting a semicolon there, and when I press enter, that method will run. Now, how do we know it's run? Well, we don't really. That was kind of a bit of a class that really does nothing. So class, so we'll call that class 2, and in this class we will have public int sum. Okay, and in this method we will have int a, and okay, well, let's call it first, and int second. Okay, so this method now returns an integer. Its name is sum, and it has two formal parameters called first, which is an integer, and second, which is an integer. So this method, you might deduce from what I've written so far, produces the sum of two integers. Okay, and open the squiggly brackets to start the method body, and then what we can do is we can just say return and then an expression, so we can say first plus second. So in this case we're returning results, so the return statement needs a value to return, and it's actually the value is the result of that computation there. We can go ahead and define that class by pressing enter on the last statement, and then we can say var adder equals new instance of class 2, and we're calling the constructor, so we need the brackets there with no arguments. So now we have an instance of class 2 called adder. So now we can say adder dot sum, and you can see that the editor knows that we defined sum and it's trying to help us, so we can just select it from there, and it saves a bit of typing. Let's go with 3 and 5, so we're expecting the result to be 8, and enter. Now what happened? Nothing happened. Okay, so what actually happened here is that our sum method was called, the values 3 and 5 were passed in. Okay, these substituted for first and second. The computation here, first plus second, was carried out. The result 8 was then returned. Our value got returned, and then we didn't do anything with that value, so it just got thrown away. So if you want to use the value of a method, you either have to put it somewhere or do something else to it. So we could, for example, say var sum equals adder dot sum of 3 and 5 and semicolon and enter, and that executed. And now if we print out the value of sum, we have 8. Okay, hopefully that was clear. Okay, let's talk about statements. Now what we've actually just been doing in the C# interactive window is writing statements, and a statement is some expression of an action in a program. So for example, this line here, and it ends with a semicolon. So this is a thing for the program to do, followed by a semicolon, and every statement in C# has to end with a semicolon. There are some exceptions to that. As always, there are always exceptions to the rules, but you won't go far wrong if you end everything with a semicolon. The compiler will tell you if you don't need it anyway. Okay, so C# supports several different kinds of statement, and most of them we've already seen. Okay, first of all, we have declaration statements, and an example of that would be int thing equals 5. That's a declaration statement. It declares a variable, and in this case also initializes it, and that's called an initializer expression. Then we have expression statements, and an example of that would be this line here. So add.sum of 3, 5. Now we're invoking a method here, but that is actually part of an expression, and expressions are mathematical operations that you can evaluate and compute a result. Okay, then there are selection statements which control the flow of the program. We've seen an example of that with the if statement in the previous section. And there are iteration statements which are used to repeatedly execute part of a program, and we saw an example of that previously with the for loop. Finally, there are blocks, and C# is a block structured language, and the interesting thing about this is that anywhere you can have a statement, you can also have a block. So in using this, you can build up complicated compound statements. So an example of that would be right here, in fact, where we declared this method. That's a block. The open brace is the start of a block, and then we have one or more statements, or actually 0 or more statements, because you can have an empty block, and then the block is ended with the close brace. There's another example of that up here. Obviously, whenever you declare a method, you also have a block, which is the method body. You can just arbitrarily start a block in your code. So for example, I could just open a block on the command line here, and then do something in here. I could say console.writeLine adder.sum 7 and 2. I can do another statement in here of a different type, int z equals 42. There we go. Okay, so I've got two statements there. None of this is executed yet because I haven't closed the block. So once I press enter on the end of the block, then our block is complete, and that sequence of instructions executes, and we get 9 printed out because of the console.writeLine. This worked out the sum of 7 and 2, which is 9, sent that to console.writeLine, that wrote it out, and there's our result on the command line. What do you think will happen if we try and print Z at this point? Now, this is not obvious perhaps, but if I try and print out Z, we get an error. Z does not exist in the current context. Okay, now why doesn't Z exist? Because there it was, we declared it, and this is because of something called scope, and Z is a local variable because it's declared inside a block, and the scope of Z is only within these braces. Okay, so Z is in scope inside the block, but as soon as you come out of that block, Z no longer exists. Okay, so it's gone out of scope, so you can only access Z. I could have accessed it here, I could have put an instruction here that accessed Z, and that would have been fine, but as soon as we come out of the block, Z no longer exists. Okay, so this is one of the key ways in which data is kept hidden within the blocks where it's defined, and this is good because you want to hide your implementation details as much as possible, and that's something we'll cover again in another topic. Expressions. Expressions and expression statements can be mathematically evaluated and produce a result. Okay, so what's an example of an expression? We can type an expression directly on the command line here in the interactive window. So for example, we might enter 2 plus 5 and we get the answer 7. In an expression, you have pieces of data they get operated on, and you have operators. Now in this expression that we just typed, 2 is an operand, 5 is an operand, and plus is an operator. If you hover over it with the mouse, you can see it is int. It is actually a method which is declared as int.operator plus and takes 2 arguments, left and right, and this refers to the thing on the left and the thing on the right. And we'll talk about defining operators a bit later on, but for now, what you need to know is that each data type can define an operator to work in different ways. So for example, if you're adding 2 integers, then the integer version of plus will be used, and if you're adding 2 real numbers, then the real version of plus will be used, and so on. And if you have custom classes that you've written yourself, those classes can also define plus to mean something else. Okay, and we'll see how that's useful later. Within mathematics, in fact, there is a correct order of evaluation, and you don't simply evaluate expressions from left to right. So the acronym BODMAS, BODMAS, is often used, and that stands for brackets, order or exponentiation, raising to a power, division, multiplication, addition and subtraction. And that's a useful rule of thumb, but in programming languages there are other operators, and every operator has its own precedence, and sometimes the order is a bit surprising, so you need to keep your wits about you, and if you're in any doubt, use parentheses to force the order that you expect to happen. Okay, so for example, 2 plus 3 times 4. So what's the result of this expression? Well, according to BODMAS, we do the multiplication first. Okay, so 3 times 4 is 12, plus 2 is 14. Okay, and press enter. 14 indeed is the answer. Now if you went to actually do the 2 plus 3 first, so what you wanted was 5 times 4, which is 20, then what you need to do is use parentheses. So you use parentheses to do the 2 plus 3, and that gets parentheses, BODMAS, brackets, comes first, so the brackets, everything in brackets gets evaluated first, and then you multiply by 4, and we in fact get the answer 20. Okay, so hopefully that's clear. And I said that sometimes the order is a bit unexpected. Well, for example, 2 plus 3 times plus plus 4. Plus plus is an increment operator. I can't do this here in this context, but plus plus actually takes precedence over multiplication. So that might be a bit unexpected, because you know that multiplication takes precedence over addition, and this looks like an addition, but it's actually, because it's a unary operator, it only has a right hand side, then it actually takes precedence over multiplication. So just bear in mind, sometimes the order that you get is not quite what you expect, and you can look up the precedence of operators in the C# online documentation. And in fact, if you want to know anything at all about C#, the authoritative source is the C# language reference. We might put a link to that in the description. Okay, scope and accessibility. Now, scope is the part of a program within which a variable can be directly referenced. Now, we've seen an example of scope earlier where we defined a variable called z inside a block, and then we tried to access that variable outside the block, and it was out of scope, so we couldn't access it. Okay, so hopefully that's clear. And accessibility is the type of access allowed to a variable, class or method by other parts of the code or third-party code. The reason you need accessibility is because you really want to try to keep your implementation details private and not reveal them to other users. That's part of the solid principles of object-oriented design called the open-close principle, and we'll come back to that in a future episode. But for now, I'm going to write a class. So in the C# interactive window, I'm going to define a class called class3, and in that class I'm going to define a member, a field. It's going to be integer, it's going to be called multiplier, and we're going to give it an initial value of 4. Okay, so that's our field, and currently we haven't specified the accessibility of that field, so I'm going to go back to the beginning of the line. I'm going to make that explicitly private. Okay, so this is a private member field of the class 3. Its data type is integer, its name is multiplier, and this is the initializer expression. We've given it the value 4. And then I'm going to define a public method. So the accessibility of this method is public. It's going to return an integer. It's going to be called scale. Declare a formal parameter of type integer called input. Open a block to declare the method body, and it's going to simply return whatever the input is multiplied by multiplier. That's our class. Let's define that. So the implications of this are that we've declared this private member field called multiplier, and so no other code will be able to see this field or its value. Although we've defined a method called scale, this will be responsible for taking an input and scaling it up by some factor, but we don't reveal what the factor is, so no other code will know what the factor is. So we've kind of encapsulated that little piece of logic in a private member of our class, and other external code can't get at that detail. So that's called data hiding. That's part of a technique called encapsulation, and it's part of the open-close principle of the solid principles of object-oriented design. So let's see how we might use that class. Well, first of all, let's new up the class. So we're going to create a new variable called scalar, and it's going to be equal to a new instance of class 3. You remember I said that every class has a constructor, and this is called the default public constructor because it's what's provided by the compiler, because we didn't provide a constructor. So that's why you have to have these parentheses here. So now we have our scalar variable. If I hover over the var here with my mouse, you can see in the pop-up there it tells me what type has been inferred. The compiler infers the type by looking on the right hand side of the equals and working out what that expression returns as its result, and then that becomes the type of the variable here. So scalar is of type class 3. If we type in scalar dot to see what members scalar has, you can see that there is here a scale method defined, and this is the method we defined here. What you'll also see is that there is no multiplier because we declared multiplier as private, and therefore it does not come up here as something that we can access. Move down on using the down arrow key here to move to scale and press enter, and that fills that in for me. Scalar.scale, and then we can pass in the argument 4. The result of that should be 16, yes? Okay, and there's a result 16. So hopefully that's clear now, the difference between private and public accessibility. There are other types of accessibility. There's also internal, which means something is visible to everything within the same project. And there is also protected, which means it's visible to the class where it's defined and any derived classes that inherit from that class, but not other classes that don't inherit from it. So those are kind of a little bit more unusual, but they are still fairly common, so no doubt we will come across those in a future episode. In general, variables are only in scope in the block they're defined in. So we saw that earlier where we just opened a random block. Let's do it again. And then we will say console.writeLine z times 3. Clearly z is accessible from here. It's in scope. Okay, we'll define that block and execute it, and that gives us the answer 12. And if I try to print z here, there is no z, it's just not in scope, and we get an error if we try to use it. Local variables, z is a local variable here, they're in scope only within the block where they're defined. Okay, that was a lot to learn, and hopefully as we go on to write code now, it will start to make more sense. So it's time to write the code that we're going to write in this episode. We're going to produce a program that emulates the game called FizzBuzz. Now FizzBuzz is a game that you might have played at school, and and typically it's a nice party game for kids, and everyone sits in a circle, and you start from 1, so the first person says 1, and then you move around the circle, the next person says 2, and so on. But the third person, rather than saying 3, has to say fizz, and the rules are that any number that's divisible by 3, then you have to say fizz instead of the number. And so then the next person says 4, and the next person, instead of saying 5, says buzz, and the rule is that if a number is divisible by 5, you have to say buzz. Instead of 6, that's fizz, because 6 is divisible by 3. 7 is prime, so that person says 7, then you get 8, then you get fizz, because 9 is divisible by 3, and then you get buzz, because 10 is divisible by 5, and so on, until you get up to 15, which is divisible by 3 and 5, and then that person has to say FizzBuzz, and so you go on. And if you say the wrong thing, you're out, and the game goes on until there's only one person left, and they're the winner. That's the code we're going to write. We're going to use test-driven development, and we're going to use all the skills that we've just learned in the first part of the episode. So onward to the code. Okay, in our FizzBuzz folder, I'm going to right-click the folder, and I'm going to create 3 projects in here, and this may seem a bit like overkill for such a small program. Most people at this stage would just pile everything into one project, but it does establish a pattern for larger programs, so I think it's worth doing, even though it is definitely overkill. New project, and we're going to create a project for our unit test, just solely for our unit tests. In order to run unit tests, we need a .NET framework class library. So we're going to use C# in the language filter here. Under all platforms, we're going to go with Windows, and we're going to use library in this filter here. Our first option is class library.NET standard. Well, that's not quite what we want. What we actually want is this one here, class library.NET framework and C# language. So we'll go ahead and create that, and we will name it ta.code like a ninja FizzBuzz.test. Okay, so I've got a 4-part name here. That's perfectly fine. And the directory here the default should be fine. You shouldn't need to change that. And in the framework here, that should be .NET 4.7.2. It doesn't matter if it isn't, just use the highest one you've got, but it should be 4.7.2 at this point. So go ahead and create that. And this will be our unit test project. Now, one thing I like to do with a new project is get rid of this default class1.cs file that the template creates. It's kind of nice the first time you ever create a project, but after that it kind of pokes you in the eye, and nobody ever uses it, so just delete that. Now we need a project for our game logic. So I'm putting all the what would be called business logic into its own separate class library. So add new project, and for the logic, I want this to be usable from as many places as possible. So what I'm actually going to do here is use a net standard library. So in .NET you have the concept of platforms. So .NET Core is a platform, .NET Framework is a platform, Windows Universal Runtime is a platform, ASP.NET Web is a platform. And they all have their own ways of, application models, and in some cases their own standards for creating libraries. But a net standard library is relatively new and actually works in any of those platforms. So that's a really useful choice to make here. So we're creating a class library, brackets .NET standard, language C#. And this means we'll be able to use our game logic from any of the platforms I mentioned. And we're naming this TA code like a ninja .fizzbuzz let's call it game logic. Okay, and what I'm establishing here is a really common pattern for application development called a 3-tier application, where you would have a data access layer at the bottom, and then in the middle you have a business logic layer, and on top of that you have a presentation layer, which is your user interface. So we don't have a data access layer because we don't have a database or anything, but the game logic project is our business logic layer. Okay, and we may come across those terms again in later episodes. The third project I'm not going to create yet, that will be our presentation layer. But for now, looking at the test project, we need to install a unit test framework so that we can actually write our tests and a means to run the tests. The way to do that is to right click on the references node here and select manage NuGet packages. Now NuGet is an online service where other people can write libraries and put them onto NuGet, and it's like a central repository of .NET libraries. Very, very useful. So here is the list of stuff that's on NuGet. We want something called machine.specifications. So I'm going to look up in my search box here, machine.specifications. We actually want this one, machine.specifications, machine.specifications.should, and machine.specifications.runner.visual studio. Okay, so I'm just going to start by installing this middle one, the machine.specifications.should, and I'm just going to click the down arrow at the end there to install that. And if you look in the output window here, this is the package manager output window, successfully installed. You want to see at the end here successfully installed. If that doesn't display, something's gone wrong. One interesting thing to note is that this package, machine.specifications.should, has a dependency on a number of things, one of which here is machine.specifications, and you'll notice that that has automatically pulled in, there we go, so we've got machine.specifications.should, and we've also got here machine.specifications. So the thing under the references node here is all the third-party code that your program is using. These are also known as dependencies, and there will always be a load of these here with system dot something or other. And this is the Microsoft base class library basically. So system. When at the start of our program we say using system, this is what we're referring to here. This namespace. And so we've just brought in these two here, and the final thing we need is machine.specifications.runner.visual studio, and this is a little test runner which allows Visual Studio to discover and run our tests for us. Okay, let's write our first unit test. So I'm collapsing down the references node here, and I'm going to right click the project and select add, and I'm going to select class. Okay, it's easier to do this than renaming class1.cs, honestly. So I'm going to call this class, there's actually going to be more than one class in this file, so I'm going to call this game logic tests. Okay, game logic tests, just like that. Okay, and the big characters you see popping up there are just telling you what characters I'm pressing on my keyboard. Okay, I'm going to minimize the error window here because we don't need to see that. Here is our class. The editor's generated an empty class template for us, and I'm not going to actually call it game logic tests. I'm going to call this class when the number is not divisible by 3 or 5. Okay, so this is sort of one of our game rules. I'm naming this class after one of our game rules. When the number is not divisible by 3 or 5. In unit tests, we follow something called the AAA pattern. Okay, so the AAA pattern, which is arrange, act, and assert. Okay, and the double slash character I'm putting in there is a single line comment, so that means anything that follows that double slash is just simply ignored by the compiler. So this is documentation for you, the developer, or for another person trying to understand your program. And so we need to write a test using this pattern. Now in the mspec, machine.specification, we call that mspec for short, in that framework this takes the form of an establish context. Now I'm not going to fill these in yet. Okay, so notice, the first thing to notice here is the editor's trying to help us again, and it's given us a red wavy underline under establish, and this means that the compiler's given an error for that line, and it's narrowed it down to exactly what the problem is. So type or namespace establish could not be found. Are you missing a using directive or assembly reference? We've got our assembly reference here under references. Sorry, there we go. Machine.specifications, that's the reference we need. So we're probably missing a using statement. And anytime you see one of these little pop-up light bulbs, you can type Control Dot on the keyboard, and Visual Studio will pop up a list of suggestions for what it thinks might fix the problem. So in fact, this first one here is exactly what we want, using the machine.specifications. So we'll click that, and Visual Studio has added at the top here this using statement, which now means that we can access this establish type. Okay, so we can have an establish context. The act phase is a because, so because of something, and then in the assert phase of our test we will say it should return the number as a string. Hopefully you're getting the idea of how these unit tests work now. So I'm going to just delete that comment there because that doesn't really help. Arrange. Our arrange phase is not defined yet. Let's define that now. This construct usually makes your eyes bleed the first time you see it, so don't worry about exactly what this means. It's kind of an advanced concept that we will cover later on, but for now, if you just sort of squint at this and try and read it in English and ignore all the funny characters, it hopefully should make sense. So establish context is going to be, in order to establish our test context, all we're going to do is new up an instance of our GameLogic class. So we will say unit under test equals new FizzBuzzer. Okay, I'm going to call the GameLogic class FizzBuzzer. And now obviously we've got lots of errors here, so let me just scroll out a bit so we can see the whole line. This thing which doesn't exist and this thing which doesn't exist. Okay, so the first thing I'm going to do is create this FizzBuzzer. Okay, now I want to create that in my GameLogic project because this is going to be the real production code now. One of the reasons for doing it like this is to keep the unit tests separate from the code that's actually the code that you want to write, so that when it comes to installing it or something, all the unit tests just go away because you just leave those out in their own separate project. The reason for putting the GameLogic in a separate project like this is because it makes it easy to split apart from the user interface, and it makes it easier to unit test. Okay, so this is a really good pattern to get used to following, and we will create a new item in here, a new class, okay, and the name of the class will be FizzBuzzer. And you don't have to put the .cs. If you don't put the .cs, then that will be assumed and put on for you because it knows you're creating a class. So that's just a useful shortcut. And here we go. So class FizzBuzzer, we need to make that class public, otherwise our unit tests won't be able to see it. Actually, there is another way to do this, but for now we'll just make it public. So we've got a public class FizzBuzzer. It's a degenerate class, it doesn't do anything, and that's fine for the moment. I've got a rogue class1.cs there, which I'm just going to get rid of. Delete, delete. Now we've got our FizzBuzzer class, so I'm switching back to the unit test file using the tabs at the top of the editor here. Now this has still got a red squiggly underline, but if you now use the control dot trick, add reference to TA code like a ninja FizzBuzz GameLogic. Perfect, that's exactly what we want. So that goes green, that's a valid reference now. If you look at the top, we've added a using statement for our GameLogic, and if you look in the dependencies of the unit test, we now have a reference here to TA code like a ninja FizzBuzz GameLogic. Okay, so we've referenced our other project, so everything's linked, and we've still got this red squiggly underline under unit under test. So what we actually want here is a field in this class when the number is not divisible by 3 or 5. This needs to become a class member because we will need to access it later. And so I'm using control dot again, and notice that this is a pop-out list. So if we go over here, one of the options we've got here is generate field. So I'm going to click generate field. It's generated this private static field called unit under test, and it's of type FizzBuzz, which is the empty class we just defined in the other project. And static, we haven't covered what static is yet. We'll come back to that in another episode, so we'll just gloss over that for the moment. But this is just for now, except this is just the way you have to do it for the sake of the unit test framework. What you'll notice here is that our unit test has already started to drive how we write the code, and this is why it's called test driven development, because the first thing it caused us to do was to create this class, our unit under test. This is the idea of unit testing, is that the name unit testing is something of a misnomer, because I would argue it's actually more of a design technique than a test technique, with the added side effect benefit that you actually do get tests out the end of it as well. So our act phase, again we're going to have this little funny sequence of symbols here. This is actually a lambda expression. If any of you are keen enough to go off and research that, you don't need to know how they work for now, but just know that the unit test framework will run these at the correct time. So in our because of clause, we are going to actually exercise the class under test and get a result back. So we want our actual result that we got back equals unit under test dot apply game rules, and the number we will give it is 7. Now 7 is a prime number, so it is by definition not divisible by 3 or 5, and so this matches the condition of our test. When the number is not divisible by 3 or 5, 7 is not divisible by 3 or 5. We will use the control dot trick to create our actual field. So generate variable, generate field. The editor has suggested object here, and object is the root thing that all types in .NET derive from, and the reason it's suggested object is because it couldn't work out what the right hand side of the equal sign was, what type this expression evaluates to a result of a certain type, but because we haven't written apply game rules yet, the compiler and editor are not able to figure out what type we mean, so it's just defaulted to object. Okay, so we're going to override that and make it an integer or int. Okay, and then because I've done that, you'll see that if we use control dot on this error here, it's now offering to generate the method FizzBuzz.apply game rules, and when we select that, that's now gone. The squiggly underline's gone, so we've no longer got an error. And if we hover over that, if I hover our mouse over that and hold down the control key at the same time, you'll see it turns into a hyperlink, okay? And then if you click that hyperlink, it will take you right to the code that's been defined. So this is in our FizzBuzz class, and now we've got public int apply game rules int v. So the editor was able to work out it was a method that has an integer parameter and returns an integer, so it's put that method signature in for us by default, which is very handy. And we will just give this thing here a more meaningful name, so we'll just call that number. The line that it's put in here for us just causes an error. Basically that makes the program gives you an error. It obviously won't be what we want, but the rule in unit testing is you shouldn't write any code until the test mandates it, so we won't do anything here for the moment. And we'll just switch back to our test class, and so this is good, there's no errors here. So now we want to make assertions on the data we got back. So I'm just going to create another field here called private const string expected. I'm just going to initialize that to 7 in quotes. Now it's important to realize that 7 in quotes is a string, whereas 7 on its own without the quotes is a number. Okay, and that's actually an error. You can see there's a red squiggle there because I've declared this as a string and then given it a number. Now C# is strongly typed, and so it means that you have to get the type of everything correct, and the compiler will not simply convert this for you like it will in some languages. You have to actually tell it by using double quotes, this is a string, actually a string containing the character for 7. The const keyword here is new. We haven't seen that before. That just means constant, which means this thing I'm declaring here will always have the value 7 in quotes and can never change. If you try to modify this in your program, you'll get a compile error. Okay, so if you intend something to be a constant, declare it as a constant. That's good practice. And then in our assertion here, we're going to make the assertion. We have to do this little incantation. Then we will make the assertion, okay, that the actual result dot should equal the expected result. Now I've got a red squiggly underline here, so let's just, alright, so what's going on here is that if we hover over this thing here, we've got this field. If you can see the pop-up, I'm going to just use the magnifier to zoom in on this because it's a bit hard to see. So if I hover over actual here, you can see that that's a field and it's of type static int. Its signature is static int when the number is not divisible by 3 or 5 dot actual. So this is an int, okay? And then expected over here, not that we can see it, there we go. Expected is a string. So I'm trying to compare an integer to a string, and the compiler is complaining about that, okay? Which is fair enough because you can't directly compare an integer to a string. So why is that? My expected result here is a string, that's correct. So this must be wrong, okay? So actual is an int. Okay, there's our problem. So this should have been string all along, okay? And then we're going to get an error because now this has got the wrong type. So let's control click this to navigate to it, and we want to make this a string. It needs to return a string type. We're all good. Now we've got no red squiggly underline here. So let's just look at this line again. So this is the name of our test. It should return the number as a string, and then that's defined as, if you just read this group of symbols here to mean is defined as, then actual should equal expected, which seems fair enough, right? So the actual result we got back should equal the result we expected, and should equal is a method provided by the unit test framework which does this comparison. Okay, and now we should be able to run this test because there's no compile errors. So if we go under the view menu and look for test explorer, there we go, and here's our test explorer window at the bottom, and the compiler should take a minute to warm up, and then it will look through our code to try and find any tests we've got. There we go, it's fired up and it's saying build your solution to discover all available tests. Okay, so to build a solution you can go up here to the build menu and click build solution. Okay, that's showing us Control-Shift-B would have worked. You can see the little animated icon down here, which means there's a build in progress, and the progress bar there. Build succeeded here, so we've got no errors. Now the unit test explorer is introspecting the code and it has found our test, so we can expand that, and as you can see, here's our test name, when the number is not divisible by 3 or 5. And if we expand that, when the number is not divisible by 3 or 5, it should return the number as a string. And as you can see, this comes out in English and reads as an English sentence. And this is why we use this kind of slightly funny naming convention. Okay, so the unit tests make sense when you read the results. When the number is not divisible by 3 or 5, it should return the number as a string. This is currently indeterminate. This thing here means the test has not been run. So we can run the test by clicking the run button here. So our test has failed. Now we expected it to fail because we haven't written the code yet, okay? And should return a number or the number as a string. The method or operation is not implemented. This was the error message, okay? And if you look in the window off to the right here, I'm just resizing that. You can see that we got, here's the message, the method or operation is not implemented. And the reason that happened is because if we look in our FizzBuzzer class here, it threw a not implemented exception. Okay, and exceptions is something we'll cover later, but just know that's a program error. So I'm going to delete that first of all and then rerun the tests. The reason there's a build error here is because, as you can see in the little pop-up box here, FizzBuzzer.apply game rules, not all code paths return a value, and we've defined this method as returning a string, and then we haven't returned a string, so obviously that's an error and the compiler doesn't like it. So the simplest way to fix that, what I'm doing here is making the simplest code changes I can to make the test pass. Okay, so I'm just going to return an empty string for the first attempt, and we will rerun the test here. Now, we don't get an error this time, but we expected a string length 1, but was 0. Okay, over here, strings differ at index 0. Expected 7, but was empty. Okay, so we can see exactly why our test failed. And what I'm doing here is a little loop which is really common in unit testing called red-green refactor. And when you write your unit test, you must see it fail. If you do not see your test fail, you cannot be sure that it's actually testing the thing you think you're testing. So that's the red phase, and it comes from the color of the icons here in the unit test runner. A red test is failed. And then you do the simplest thing you can to make that test turn green. And if you've written your test correctly, that means it's returning the correct results, right? So we'll return now the literal value 7 and rerun the test, and there we go, the tests have gone green. So we're now in the green phase of our test, and we now need to do the refactor phase, which is to do it right. Okay, so we did the simplest thing to make the test passed. All sins are allowed. You can do the nastiest, hackiest, dirtiest piece of code you ever wrote, that's fine, but what you must then do is, once you've got the test to turn green, you must refactor it, which just means change the code to actually do it right. So obviously we want this to work for more than just the number 7. We want it to work for any number that's not divisible by 3 or 5. So actually what we want, we've got the number being passed into us here as an input argument, and so what we actually want is to just convert this to a string and return it. Okay, and every object in .NET has a toString method, so we can just say number dot toString. Okay, and that converts whatever number is, in this case it happens to be an int, to a string representation of that object, and then because that's on a return statement, it returns it as the result of the method. Now if we run our test, okay, we're still green, which means we didn't break anything, and that's an important confidence indication. And so what we did in the red-green refactor loop is we wrote a test, we saw it fail, which means that we can be sure we are actually testing something, and we turned it green, and what that does is it fixes the behavior that we wish to see from our code. and then we refactor to do the code right, and if the test stays green at the end of it, it means we've still got the right behavior and we haven't broken the rules. Okay, so that's our first unit test. Normally this loop would go very, very quickly, so I'll move straight on now to our second unit test. Okay, so hopefully that's not too frightening, and it will make a bit more sense as we do the second unit test, so let's go right ahead and do that. So switching to our unit test class here, you should be a bit wary of using copy and paste when you're writing code, but I'm actually going to do that in this case. And so Control C and Control V, and okay, so I'm actually creating a second class in the same file now. I'm going to say when the number is divisible by 3. So this is the game rule that we're testing, and so the expected result now is 3. All this is going to be the same, except we're going to pass in 3 instead of 7, and we expect to get 3 back. No, we don't expect to get 3 back, we expect to get fizz back, don't we? Okay, fizz is what we expect to get back, because that's the game rule. When the number is divisible by 3, it should return fizz. Okay, it should return fizz. When we go ahead and run that test, remember red-green refactor, we expect to see this test fail. It's one of the few situations where you are glad to see an error, so make the most of it. Okay, not run, that's interesting. Why is it not run? Oh, because, okay, so when you click the run button here, this only runs the test that you've got selected. So if you want to run all the tests, you need to click this other button here, Control RA for run all. And as you can see, our original test still passes, but our new test fails. Let's now go ahead and make that test pass. Now, the simplest thing to do to make that test pass would be to return the text fizz. Okay, and that's fine, but when I run that, we should discover that that test now passes, but our other test fails because I deliberately overwrote the correct code that we already wrote. Oh, and they in fact both fail because I should have returned fizz with a capital F. Okay. The point I wanted to make there was that I broke my other test, so I can't do this. This is bad code because it broke a test. So we've got to do things a different way. There we go. So my original test failed now, and because it expected 7 but got fizz, because everything's getting fizz now. So I'm going to actually undo that change, and Control Z is undo, so I'm putting back the original code there. We've seen an if statement before, so we can use if to alter the program flow depending on value of number. So the test we want in here is something that says, is the number divisible by 3? One technique you can use for working out if something is exactly divisible by something else is to use something called a modulus operator, and in C# that is a %sign, and modulus divides one number by the other and gives you the remainder. And so if the remainder is 0, then we know that it was exactly divisible because there's no remainder. Okay, so we can say if number modulo 3 is equal to 0, and notice I've used a double equal sign to test equality. Assignment is a single equals and equality is a double equals, and this is a really common mistake in C-type languages. Always make sure you use this double equals when you're testing equality. So if the number modulo 3, in other words the remainder when the number is divided by 3, is equal to 0, then, normally you put the then part on another line, we will then return fizz. And because we've got a return statement here, that's the end of the method. It doesn't drop through and then execute this other return statement, because you can only return once from a method. Okay, so as soon as you've returned, the method's finished. So that hopefully should make both of our tests pass. Okay, that's good. We've got all green tests, so we're in a good shape here. Now, for the refactor phase, I actually don't need to do anything for this test because it was the actual quick and dirty piece of code was the right answer in this case, so there's nothing to refactor. So this is fine. Hopefully this will speed up a bit now, so we'll go on now and do another test. Okay, time for another test, and switching back to our test project, I'm going to select all the lines of this test and Control-C, Control-V, Control-V. What I did there was paste it twice. The first time I pasted over-typed the selected text, and then the second time pasted a new copy in. So when the number is divisible by 5, we expect to get buzz, and we pass in 5. Okay, so now we're really going. We've just written a whole new test. We run that. We expect it to fail. Okay, good. When the number is divisible by 5 has failed, and the reason it failed is because it expected buzz but was 5. Okay, so in fact the name is wrong here. This is one of the hazards of copy and paste coding, which is why it's a bad idea to do it. But it should return buzz. You want the name of the thing here to make sense when you read it in English. So currently this is wrong here. If I rebuild this and run the tests again, when the number is divisible by 5, it should return buzz. Perfect. It's failing. So we switch over to our code. The test is now pushing us to write the correct code. So we can say another if statement here. So if it wasn't divisible by 3, then we need to check if it's divisible by 5. So we can do the same thing. So if number modulo 5 equals 0, then we will return buzz and run our tests, and that should pass. And there we go, green bar. Green across the board, and so that code is correct. And we'll go straight on to write our final test, which again I'm going to just copy this code, copy, and then open up a new line and paste it. And when the number is divisible by 3 and 5, then we expect to get FizzBuzz. So when we pass in the first number that's divisible by 3 and 5 is 15, it should return FizzBuzz. That should fail. Okay, so when the number is divisible by 3 and 5, failed, one failed. Why did it fail? Let's have a look. It failed because expected FizzBuzz but got fizz. Okay, so now we need to fix this. Now we need to do if the number is divisible by 3 and 5, then return FizzBuzz. Now we can't do it here because the code would detect the divisible by 3 condition first and still return fizz. So we need to do this more specific check before the less specific checks. So we need to do it right up here at the top. So if number is divisible by 3, and we're going to use a new thing here that you haven't seen before, which is a logical AND condition. So that's 2 ampersand symbols. That means logical AND. If the thing on the left is true and the thing on the right is true, then the whole expression is true. The thing on the right is going to be number is exactly divisible by 5. Then if that condition is true, then we return FizzBuzz. And run the tests and see if we've made it pass. And more importantly, that we haven't broken any of the other tests. Okay, and all our tests are green, so we have now correct program behavior as defined by our game rules. So that's fully working, and now we have the refactor phase. Don't forget the refactor phase. So what I'm going to do at this point is look at this code and say, does that really make sense? Would someone who hasn't seen this code before be able to come in here and instantly understand what it does. And I would argue it's a little bit opaque because, and it's a little bit inefficient too, because we're doing this test here, we're doing that computation here, and we're doing it here as well, which is repeating the same thing twice. Now, there's a general principle in coding called the dry principle. Don't repeat yourself, the dry principle, which means that you really want to only have one source of the truth if possible. So we've done this same calculation twice, but if for some reason I was making an edit later on and I changed one of these and forgot to change the other one, then there's a bug there that I would have. So ideally, you only want to do these things once if possible. It's good for efficiency, but more importantly, it will be better for readability and maintainability. So we're trying to drive towards clean code that other people can understand. Okay, as Donald Knuth said in his books, The Art of Computer Programming, a computer program is a way of telling another person what you want the computer to do. Okay, and that's not what a lot of people think a computer program is, but I like Donald Knuth's definition. So what we're going to do is just change this around a bit and try to make it a bit more readable. Now I'm just going to have a look at control dot here, and one of the things we can do here is introduce a local variable. Okay, so we can pull out a local variable for all occurrences of number %3 equals 0. So I'm going to click that, and that's a refactoring tool that's built into Visual Studio. And notice that it's pulled out that code from where it was to here, from both places it was used, so from there and there. It's created this variable of type Boolean, bool, which is a truth variable. It can only be true or false. And it's named it V, and it's put the cursor on the V so that we can overtype it with the name we want. Okay, so I'm going to give it the name is divisible by 3. Okay, is divisible by 3. Okay, right, so hopefully now let's rerun the unit tests at this point to check that that's okay and we didn't break the code. So the unit tests are running. There they go, and everything's still green, so we're still good. We still have correct behavior. This now, I think, I don't know if you agree with me, but I certainly think this now is easier to read, because you know exactly, this one in particular, if is divisible by 3, return fizz. That kind of tells you exactly what we're doing here, rather than having this opaque thing here, which you might happen to know how modulo works, because I've just told you, but in 6 months when you look at this code, you might not know what the hell's going on here. But because we've got this variable now called is divisible by 3, it should be transparently clear what's going on there. And this is a practice you really want to push for in your code. It helps other people read your code. It will help you read your code. It will make the code easier to maintain, because no code stays static. I mean, you need to edit code quite a lot. And it's really kind of helpful if you can understand it easily. Okay, so I'm going to do exactly the same process for this part here, the is divisible by 5 part, and we'll use control dot to get the refactoring tool up. We want to introduce a local variable for all occurrences of that expression, and that pulls it out. We want to rename it to is divisible by 5, like that. Okay, and there we go. Run the tests again, make sure we didn't break anything. Okay, all our tests are still green, so we still have correct behavior. We didn't break the code, and I hope you agree that is easier to read now. We're not repeating this computation, we do it once only. We use that result here, and we use the results here again. So we're following the dry principle. We didn't repeat ourselves, and we made the code cleaner and easier to read. So that was a good refactor, and our game logic is now finished. So we'll go on now to write a tiny user interface layer. Alright, so all our unit tests passed, we've finished our game logic, and what we need to do now is make this into a runnable program so we can actually see it run. If we go ahead and create another project in our FizzBuzz folder, add a new project, and we will call this, we want a, not a library this time, but a console application. Okay, and we have a console app.NET Core, will do fine. Next, and we'll call this ta.code like a ninja.fizzbuzz. The directory again should be fine. Click create, and here is our program. Now you've seen this before in Hello World. This is the default runnable program. We have a class for our program. Again, we could call this FizzBuzz program if we wanted, and I'll do that just to emphasize the fact that there's nothing special about that name. We have our main method, which is the program entry point. This is where the operating system starts the program running, and it passes in command line arguments. Now, if you're not going to use command line arguments, you don't actually need to have these here. So I'm just going to delete them just to stress the point that we're not using them. Okay, it's good to be explicit about things if you can, and not just programming by accident or by implication is generally to be avoided, because you want to make it obvious what you're doing and what your intent was. So I intend not to use command line arguments, and therefore I've removed them from my main method. Okay, so we don't want console.writeline hello world, we want some other code. Okay, and the first thing we're going to do is create an instance of our game logic. So we can say var. Remember, var is a keyword which tells the compiler to infer the type of the variable you're defining. So we're going to call that game logic. Why not? And the convention here for a local variable is to use what's called camel case. In other words, it starts with a small letter and then you capitalize each word as you go. Okay, so var game logic equals new FizzBuzzer. The editor isn't able to see FizzBuzzer here at the moment. It's not suggesting it, and that's because we haven't yet referenced that project. So I'm going to actually manually complete this line, and then I'm going to use control dot and see if we get the suggestion, and we do here. Look, add reference to TA code like a ninja FizzBuzz game logic. That's exactly what we want. Perfect. And Visual Studio adds the reference to our project. It's now under the dependencies node, projects, there it is, reference to our other project, and it has added the namespace up here so we can use the objects in that project. Okay, so now the error's gone away. We've got an instance of our FizzBuzzer class. Okay, and then we have to decide, let's just say we want to do the numbers from 1 to 100, okay, and apply FizzBuzz rules to the numbers from 1 to 100. So we've seen a for loop before briefly when I talked about iteration. So the syntax of a for loop is, okay, it's basically like this, okay, and the thing here in this position is the initialization for the loop. So this is where you set the starting state for the loop. In here you'll perform a test and the loop continues while that test is true, and then in here you do some action at the end. If every time you go around the loop at the end you perform this action. Okay, so we can say int number equals 1. So that's the starting condition. We want to start with the number being 1. And then we want to do this loop while number is less than or equal to 100, because we want 100 to be included. So number is less than or equal to 100. So while the number is less than or equal to 100, we will go around the loop. And then at the end of the loop, we want to increment number. So plus plus number. Okay, plus plus is the increment operator, and it can go there where I've put it, or it can go here at the end, and that's called post increment, and this is called pre-increment. And there is a subtle difference between the two, which I probably won't cover now. I'll cover that when we look at expressions in more detail. We don't actually need that semicolon on the end, so that's a syntax error. And there we go. So that there's no red squigglies here, so this is valid syntax. The compiler's happy. What do we want to do in the loop? Well, first of all, we want to get the result back from our game logic. So I'm going to create a new variable, a new local variable indeed, called FizzBuzz, and I'm going to set that to. So we want to use the game logic instance of the FizzBuzzer class that we created, and then dot to access the members, and then apply game rules. So we're invoking the apply game rules method member of the game logic instance of the FizzBuzzer class. And then to our method, we need to supply an argument, and the argument is going to be number, which is the index variable of the loop here. What happens is whatever value number is this time round the loop gets passed into this method. The result comes back as a string that gets stored into the FizzBuzz local variable, and if I hover over var, you can see that's a system.string, and it knows that because apply game rules returns a system.string. And once we've got our result, then we can just write it out on the console. Okay, so console, and obviously it might be obvious now that console is a class that's defined by the system, so we can use dot to access its members, and WriteLine is a method member of that class, and so we can then supply the thing that we want to write out to the console, and that is FizzBuzz. Okay, the variable FizzBuzz that we created here. Notice that we used WriteLine, so what that means is, as you can see from the comment text here in the pop-up, writes the specified string value followed by the current line terminator to the standard output stream. Now in a console application, the standard output stream is the console itself, so we should see that on the screen. Let's go ahead and build that. Okay, good, no compiler errors. Build succeeded down here in the status bar. We want to run this now, and in order to run in Visual Studio, we need to tell Visual Studio which project we want it to run when we tell it to run something. Now currently that is our Hello World program here. You can see that that's in slightly bold type. That means it's the default project. Okay, so what we can do is we can right click, we can come down to set as startup projects, and then you notice that this project is now bold, which means it's the default project. So we can now click start in the debugger up here, and we should see a console window. The debugger is starting up. It does take a few moments. Okay, and there we go. There are our results, all the numbers from 1 to 100 with FizzBuzz rules applied. And we just scroll back a bit in the scroll back buffer here, right back down to 1. So 1, 2, fizz, 4, buzz, 5 was buzz, 6 was fizz, 7, 8, 9 was fizz, 10 was buzz, 11, 12 was fizz, 13, 14, 15 was FizzBuzz. Okay, so our game is working. Okay, we wrote our first program. We did it with test-driven development, test first, and we set a few useful patterns for doing bigger projects. Hopefully that all makes sense. I will be around to answer questions in the comments. Please let me know if you liked the episode. Please let me know if there's any questions you have or if there's anything you'd like me to cover specifically. And I hope you learned something. If you thought I've earned it, then please consider subscribing to the channel and maybe supporting us on our Buy Me a Cup of Coffee page on the website, which is linked below. I've been Tim from Tiger Astronomy. Thanks for watching. See you in the next episode. Right, whoa, don't turn off. There's an Easter egg. I want to show you something cool. Okay, so a couple of times during the video you'll have heard a little background riff playing when I was talking about FizzBuzz, and that was actually the FizzBuzz riff, and it was created using this program called Sonic Pi by Sam Aaron. This actually runs on a Raspberry Pi as well as on Windows and Linux, and it's a little sort of live performance synth for coders, so you basically play it by writing code, not by using a keyboard or anything. So here's a little bit of code I've preloaded, and I'll just start this going. And so this is just basically doing a 16-beat bar and playing this note A1 continuously. And then we can add some cymbals to that by just doing something like that, and start that again. And notice everything syncs up nicely. Okay, and then we can add a drum loop to that. So on the end here, just paste a bit more code, a drum loop. Okay. Alright, and then what we can do is we can take I said it was a 16-beat bar, so we can take the beat number of the bar and we can apply FizzBuzz to the beat number, and then depending on whether it's divisible by 3 or 5 or 3 and 5, play a different note. So I'm going to replace that line there with a few if conditions. There we go, and just tidy up and start that again, and we have the FizzBuzz riff. Okay, that's nothing to do with C#. I just thought you might think that was pretty cool, so hope you liked it. That's the end of the Easter egg.